All right, everybody. Welcome back. We are ready for another deep dive. And this one is going to be a good one, I think. This paper is called Titans, Learning to Memorize at Test Time.
Ooh, that's a good one.
It is a good one. This is from Ali Barouz, Palin Zong, and Vamab Marokni at Google Research. And as always, we'll have a link to the paper in the show notes.
Right.
But yeah, this paper really tackles, I think, something that's kind of been a thorn in the side of AI for quite a while.
Yeah.
Which is, how do we make models that actually memorize things long term in a way that is actually useful?
Yeah, we have these great architectures now, like transformers, which are great at in-context learning, but their memory window is only so big.
Okay, it's expensive.
And it's really expensive. That quadratic cost is just a killer.
Yeah, right. And we've seen attempts to address this, like linear transformers trying to be a little bit more like recurrent networks by using like these kernel tricks, but then you end up with the classic problem of trying to compress so much information into such a small space.
Like trying to fit an encyclopedia into a matchbox. You can get it all in there, but good luck finding anything.
Exactly.
I think what's really cool about this Titans paper is that they sort of take a step back and say, hey, what about how human memory works? Like maybe that's what's missing.
Yeah, they're looking at our short-term memory and our working memory and long-term memory and how all these different systems work together.
Right. And so they pose these three really interesting questions. One is, what is a good structure for this?
Like, if we're going to have memory in an AI system, what does that even look like?
What does that look like? And then two, how do we update that memory as the model learns?
Yeah, because obviously our brains are constantly learning and changing over time.
Right.
So how do you actually implement that?
Yeah, how do we make sure that the model is remembering the right things and forgetting the things that are not so important? And then the third question, which I think is also really important, is, okay, we have this memory. How do we actually retrieve information from it?
In a way that makes sense.
Right, efficiently.
That's right. So they introduce this idea of a deep neural long-term memory module.
Right. And this is really the heart of their innovation, I think.
Yeah, but this isn't just like another layer in a neural network. This is like a meta model, right? Yeah. It's learning how to memorize.
It's learning how to memorize at test time.
It's crazy.
And one of the key mechanisms they use for this is this concept of a surprise metric.
And that's based on gradients, right?
Yeah.
So the model figures out what to remember based on how unexpected the new information is.
Right. If it's something that it already knows, it's like, okay, I'll just forget about that.
Yeah, I've seen this before. No big deal.
If it's something that's really surprising, then it's like, wait a minute, I need to remember this. This is important.
I love that they draw this parallel to momentum in gradient descent.
Oh, yeah.
So like past surprise, affects what the model considers important going forward.
Right. It's like, the model is building up this intuition about what kinds of things are worth remembering based on its past experiences.
Yeah, it makes a lot of sense. And like our brains, this neural memory has a forgetting mechanism.
Of course.
Which is so important for managing the memory capacity.
Right.
Right. Because you can't remember everything.
You can't remember everything, and you shouldn't remember everything.
We shouldn't. So you have to pick and choose. And it's so cool that they've built this in.
Right.
So, okay, we have this memory module, but how do they actually put it to work?
So they present three different architectures, which they call Titan architectures. And it's like they're saying, okay, we have this really cool engine. Now we're going to show you three different cars that we can build with it.
Okay, I like that analogy.
So the first one is called Memory as a Context, or MT.
I'm out.
And essentially, the memory here acts as additional information that's fed into the attention mechanism.
Oh, so it's augmenting the attention.
It's augmenting the attention.
I got you.
The second one is memory as a gate, or MAG. And here the memory works together with the sliding window attention. And they have this gate that decides how much weight to give to the output of each. So it's dynamically filtering between recent information and the long-term memory.
Cool. So it can kind of switch back and forth as needed.
Exactly. And then the final one is memory as a layer, or MLL. And here the memory actually becomes a layer within a deep neural network.
Oh, so it's processing information before it even gets to the attention mechanism.
Exactly. So it's like a pre-processing step.
Wow. I'm really curious to see how these perform.
Yeah, me too. And they actually explore using the memory module entirely without attention as well, which is really interesting.
Really? Without attention at all?
Yeah, so it's like they're really trying to push the boundaries of what's possible with this memory module. So they really put these through the ringer. tested them on a variety of tasks like language modeling, common sense reasoning, those needle in a haystack type tasks.
The ones that really test your memory.
Exactly. And I think the most impressive finding was that the Titans performed really well on these long context tasks.
This is where it shines, I guess, right?
Yeah, like the Babylon benchmark, which is specifically designed to test how well models can handle extremely long sequences.
Babylon is tough.
Yeah, and the Titans just crushed it. Like the MC variant of the Titans actually outperformed much larger models, including GPT-4, on some of these tasks.
Whoa, hold on. They beat GPT-4.
Yeah, it was pretty remarkable to see.
That's a huge accomplishment, especially for a new architecture like this.
Yeah.
It sounds like they found a way to get really good performance without just relying on, brute force model size.
Yeah, exactly. And they were also really efficient in terms of computational resources. It wasn't just about being effective, it was also about being lean and mean.
Which is huge, right? I mean, one of the biggest criticisms of transformers has been the computational costs, especially with long sequences. So how did the Titans compare in terms of training throughput?
Yeah, so they did a really thorough analysis of the training throughput of different models, comparing the Titans to, various state-of-the-art sequence models.
Okay, so how fast can these models actually learn?
Exactly. And the results were really encouraging. Like the ML variant of the Titans actually showed significantly faster training throughput than many of the baselines, including some based on architectures like Mamba and gated DeltaNet.
Wow. That's pretty impressive, especially considering they have this whole deep memory module. You'd think that would slow things down.
Right, but they actually use flash attention, which is known to be very fast and efficient.
Ah, so they've really optimized it.
Yeah, they've really thought about the whole system, not just the individual components.
So let's talk about that deep memory module a little bit more. You mentioned earlier that they experimented with different memory depths, essentially changing the number of layers in the memory module.
Right.
So what did they learn from that?
Well, they found that as they increased the memory depth, the model's perplexity generally improved, especially on these longer sequences.
And for our listeners who might not be familiar, perplexity is basically a measure of how well a language model can predict the next word in a sequence.
Yeah.
Lower perplexity is better.
Exactly. And what was really interesting was that this benefit of increased memory depth was even more pronounced for smaller models. So it seems like memory depth can actually compensate for limited model size when you're dealing with these long-range dependencies in the data.
Okay, so if you have a smaller model, increasing the memory depth can really help.
Yeah, but of course there's a limit to how deep you can go. Deeper memory generally means longer training times.
It's that classic trade-off between expressiveness and efficiency.
Exactly.
You can have a more powerful model, but it might take forever to train.
Right.
Speaking of analyzing the model, they did this really cool ablation study where they basically took the neural memory module and removed one component at a time to see how it affected performance.
Yeah, it's like a surgical removal.
Yeah, exactly. So what did they find? Were there any big surprises?
Well, they found that each component they tested, including weight decay, momentum, convolutions, and persistent memory, all contributed to better performance.
So there were no freeloaders?
No freeloaders. But weight decay, which is basically the model's forgetting mechanism, had the most significant impact.
So forgetting is important.
Forgetting is crucial. If a model tries to remember everything, it's going to get bogged down.
It's like our own brains. We can't remember everything.
Exactly. We need to forget to make room for new information.
Okay, so they analyzed the individual components, but they also compared the performance of those three Titan architectures, right? The MAC, the MAG, and the ML. Those different ways of integrating the memory module.
Yeah.
So which one performed the best?
Well, MAC and MAG performed very similarly on language modeling and common sense reasoning tasks. But when they moved on to those long context, needle in a haystack tasks, MA really pulled ahead.
So when it came to those really demanding tasks, MEC was the champion.
Exactly. But it's important to note that both MC and MAG consistently outperformed the ML variant. And remember, all three of these Titans share the same core modules. It's just the way they're integrated that's different.
Right, the architecture.
The architecture makes a big difference.
And if we think back to our earlier discussion about efficiency, we see that ML, while maybe not as expressive as MA and MAG, was also faster to train.
Right.
So there's that trade-off again.
Always a trade-off.
Now, they didn't just stick to language, right? They also tested their neural memory module on tasks involving DNA modeling and time series forecasting.
They did.
So what motivated them to go beyond language?
Well, they believe that the principles behind their neural memory module could be applied to other areas as well.
So it's not just about language modeling.
It's about building more intelligent systems in general.
Okay, so what were some of the highlights from those experiments?
Well, in the DNA modeling task, they found that their memory module was competitive with state-of-the-art architectures across a variety of genomics tasks.
Wow. So it wasn't just keeping up, it was actually holding its own against models specifically designed for genomics.
Exactly.
That's impressive.
And in time series forecasting, they integrated their neural memory module into the SIMBA framework, which is specifically designed for time series forecasting.
Time series forecasting is huge.
It is, and their neural memory module actually outperformed several baselines, including those based on Mamba, transformers, and other linear models.
So they were able to improve upon an already well-established framework.
Exactly.
It sounds like this neural memory module is a real game changer.
It is. It's a really exciting development in AI.
It's so cool to see all these, biologically inspired AI systems coming out, but, no paper is perfect.
Right.
Even the authors themselves point out some limitations and areas for future work.
Yeah, like one of the things they mentioned is the computational cost of those deeper memory modules,
Right. Deeper memory might lead to better performance, but it also takes longer to train.
It's that trade-off again.
Yeah, always that trade-off. So what are some ways they think this could be improved?
Well, they suggest exploring, alternative memory architectures that might be more efficient.
Okay, so maybe finding ways to get similar performance gains without, sacrificing so much in terms of computational cost.
Exactly.
So make it a little more practical for real-world applications.
Right, and they're also really interested in exploring the integration of different memory systems,
Oh, yeah, like how our brains have, short-term memory, working memory, long-term memory.
Right, it's not just one big memory bank.
Yeah, it's a whole system.
So they see this Titans paper as kind of like a first step towards bringing that kind of layered memory system into AI.
And there's still so much we don't know about how these different memory systems could work together.
Right, like how do we make them interact in a way that's both effective and efficient? That's a big open question.
This is really exciting stuff. I mean, we're talking about AI models that could potentially learn and adapt like humans do.
Yeah, it's a really ambitious goal, but I think this paper shows that it's not impossible.
It's giving us a glimpse of what the future of AI might look like.
And it's a future that's built on this foundation of, rich, dynamic memory.
So to kind of wrap things up, I think this paper is really important because it's not just presenting a new model, it's proposing a new way of thinking about AI.
A new paradigm.
Yeah, a paradigm that embraces, the complexity of memory.
And that has the potential to, really revolutionize how we design and build intelligent systems.
It's taking us one step closer to AI that can truly learn and adapt.
And that's something to be excited about.
It definitely is. Well, thank you so much for joining me on this deep dive.
Yeah, this was a good one.
It was a good one. And as always, if you want to learn more, check out the paper in the show notes.
And let us know what you think in the comments.
Absolutely. We'll see you next time.